Hello everyone. So let us continue with the sway analysis of frames using slope deflection method. So again, in this given problem, they've asked you to analyze the given frame by slope deflection method and draw bending moment diagram. Okay, again, just by seeing the frame, you have to, the question will be as simple as this. That means here they will not specifically mention you whether it is sway analysis or non-sway analysis. Okay, then you yourself have to check and analyze. Now, how to check and analyze is, again, this is a frame which is A, B, C, and D. And then you can see here there is a load which is applied exactly at the center. And I is common at both the columns. And there is only 2I here. Okay, so 80 kilonewton. And in addition to this, there is 40 kilonewton acting here. Now, in case this 40 kilonewton wasn't there, then it only 80 kilonewton was there, then it would be a non-sway frame because it is symmetrical. Now, because there is 40 kilonewton acting here, so what happens it will try to see here, it is not symmetrical at all. So what it does is it tries to deflect, it tries to sway the frame to the right side like this. This 40 kilonewton will try to push the frame to the right side. So end A would be fixed, and B changes to B dash, C changes to C dash as such. Okay, so now this is a sway analysis. So you can analyze here. So just by seeing the problem, you have to check whether it is a sway or a non-sway. Okay, so it's a now sway analysis. Okay, because this 40 kilonewton is trying to push the complete frame to the right side, so it's a sway analysis. So for sway analysis, you have to find one more third unknown, that is delta. That is the difference between sway analysis and non-sway analysis. In non-sway analysis, you have to only find the rotations, but in sway analysis, you have to find the third unknown, that is delta here, that is horizontal displacement. Okay, then as usual, all the steps will be carried out. That is, first is fixed end moments, then is slope deflection equation, finding all the slope deflection equations, then joint equilibrium equation, and in addition to this, taking the delta value here. Okay, and then substituting the final moments. Okay, so first is the fixed end moments. So fixed end moments first, joint AB. Now you can see here there is a uh, load acting here. So just it's like you're opening this here. Okay, it's like you're opening this fixed beam here. This column opens up here, so it looks like a uh, frame with the it looks like a frame with a uh, eccentric load which is acting at a distance 1 meter. Okay, all right, so this is minus WAB square by L square. So substitute the value minus WAB square by L square. Then similarly MFBA. So it is WA square B by L square. Substitute all the values, then you'll get this value. Then MFBC. So MFBC is 80 kilonewton, which is again acting exactly at the center. So it is now minus WL by 8. Okay. Then MFCB is plus WL by 8. MFCD is equal to MFDC. There is no load acting here. So this would be 0. Okay. Next, finding the slope deflection equation. So slope deflection equation is MAB. As usual, first MAB is equal to MFAB plus 2EI by L. So the first term here is theta A. So it is 2 times theta A plus theta B minus 3 delta by L. Then theta A is fixed support, so equated to 0. And delta exists because there is a sway happening. There is a horizontal movement happening. Then substitute all the values here, and then you'll get MAB. So equation number 1. Then uh, second is MBA. Again, MBA is MFBA plus 2EI by L, then theta A, then plus 2 times theta B minus 3 delta by L. Okay. Then substitute all the values, you'll get the second equation. Likewise, third equation, MBC is equal to MFBC plus 2EI by L, 2 times theta B plus theta C minus 3 delta by L. Okay, now see here. Here what we are going to do here is 3 delta by L we are equating to 0. Why we are equating to 0? Is because only the columns are moving. Only AB and CD are moving. Okay, they're changing the position. Okay, they're changing the position like this. Initially it is straight, they're slanting. Here also, initially it is straight, it is slanting. That's why BC is not deflecting vertically downward or upward. So this delta value exists only for AB and CD. So we're equating here is, so that's why we're taking this as 3 delta by L equal to 0. Okay. All right. So now substitute all the values and this would be equation number 3. Next, MCB would be same again, MFCB plus 2EI by L, theta B plus 2 times theta C minus 3 delta by L. Substitute, this becomes equation number 4. Hmm. MCD is equal to MFCD plus 2EI by L, then 2 times theta C plus theta D minus 3 delta by L. So again, CD is deflecting. So this is 0, MFCD is 0. Substitute all the values here. Theta D is 0 because the fixed support. So this is MCD. And then finally, um, this is MDC. Mm, MDC, again substitute all the values, so you'll get, so you get 5, total 5 plus 1, 6 equations. Then we'll solve the joint equilibrium equations. So joint equilibrium would be same again, that is MBA plus MBC is equal to 0. Then MCB plus MCD equal to 0. Okay. So this is substitute all the values here, MBA and MBC. Again, main important thing is be careful, keep it in the order only, sequence wise. That is theta B plus theta C and delta equal to a constant. Then MCB plus MCD is equal to 0. So again, same thing here. Keep it in this formula, that is theta B first, theta C, then delta value equal to constant. So, you can see here, there is 1, 2 and 3 unknowns. Okay, but the equations what we have to solve this is only equation 7 and 8. So equations are only 2, but unknowns are 3. That's why we need to find another equation. We need to form another equation to find the third unknown factor. Okay, so now what we'll do to find out this, we'll take to find delta. So delta would be the sway displacement. So to find this delta, we are going to take the moment of all the forces on top of the joints of the columns only. So the columns are A, B, and C, D. So we are going to take the moment at about B and moment about C only. Okay, so just draw these two diagrams, only these two, showing all the forces and moments in it. Okay, so again, it is a fixed end. We are more interested in horizontal movement, so I'll show only RAH and RDH. Okay, and there is a moment here, MBA. Again, all the moments I'm going to assume that there are clockwise and positive, and then followed by MCD and MDC. Again, these are all positive, acting in the clockwise direction. Now, in addition to this, in the columns, there is 40 kilonewton load acting that we need to consider here. Okay. So now how do you do this is we're taking a moment about this point. So what we're going to do here is clockwise moments are positive, anti-clockwise moments are negative. So RAH, okay, we are finding moment about B. So to find moment about B, it is RAH is going in anti-clockwise. So minus RAH into 4, then plus MAB plus MBA. Again, this is going anti-clockwise, 40 kilonewton to reach B. So it is again minus 40 into 1. Okay, when you solve this, you'll get the equation as, see here, you'll get the equation as RAH is equal to MAB. So we have to keep it in the form of RAH. Only separate the RAH term here. So we have to keep it in the form of RAH. So RAH is equal to MAB plus MBA. Okay, then minus 40 into 1, which is 40, divided by the length. Okay, when you solve this, you'll get to know. Similarly, finding moment about C. So moment about C, again, clockwise positive, anti-clockwise negative. So RH is going anti-clockwise. So minus RDH into 4 plus MCD plus MDC. Okay. So if you want to find RDH, it is MCD plus MDC divided by 4. Okay. Now do you want to find horizontal equilibrium of the frames. So horizontal equilibrium of the frames is given by this RAH plus plus RDH, both are only horizontal forces. Okay, RAH plus RDH is equal to 0. Okay, we've already considered 40. So what we will do here is RH, substitute the value here. RH we already calculated here, we found out. Then RDH, this portion. Okay, then you better use the brackets here. That is easy for you to cancel. So this 4 will cancel. Okay, then you're left with, now substitute MAB and MBA. So this is MAB plus MBA. Okay, minus 40. This is resolved form here. Okay, minus 40 plus MCD plus MDC. Okay, this both are solved only and kept. Okay, otherwise what you do, substitute MCD, again rewrite once again MCD and MDC values and solve it. Then finally you're left with, again keep it in the form of theta b first, then theta c, finally delta. Okay, so now we'll get the third equation. Okay, so now 7, 8, 9 becomes the equations of equilibrium. That is 7, 8, and the ninth equation to find the delta. Ninth equation to form the delta. Okay, so again, let it be in the form of theta b, theta c, and delta, so that again when you put it back in the equation and try to solve in the calci, you'll get first theta b value, theta c value, and delta value. Be careful with the signs also here. Hmm. Okay, so now you'll get the value as EI theta b is 21.58, theta c is minus 37, and delta is minus 32. Once you get these values, substitute back in the equation, that is 1, 2, 3, 4, 5, and 6. So once you substitute, you'll get all these values. Okay, and the check is whatever you've done is right or no. The check is MBA should be equal and opposite to MBC. Likewise, MCB should be equal and opposite to that of CD. Okay, you can see here 56 minus 56. Here 24 plus 24, this is minus 25. So of course, this would be a little error, but anyhow, that is okay. It's considered as 25 only. Okay, then show it in the final frames. Show it in the final frames. That is, um, first draw the frame as such, and then mark the dotted line. So dotted line indicates the positive moment. So if the bending moment is bending inward, then I have to draw it as a positive side. Okay, if it all the moments are, if they are bending inward, then they are drawn as positive. Okay, so first moment is plus 15.35. So plus means clockwise, so this is clockwise, moving clockwise. Then clockwise, and show it on the beam, it will act on the beam. Next, similarly MBA, so BA clockwise here. Okay, this is MBA clockwise 56. Then BC minus, so in BC portion you have to show it as minus. Then MCB here is again positive, so plus clockwise. MCD is negative, so negative means this is anti-clockwise. MDC is anti-clockwise again, 6.44. Okay, so once you draw this, next is first mark this in the frame, then finally draw the free bending moment first. Free bending moment is first span AB. So span AB, there is a load, eccentric load, so WAB by L. So it is 30. So under the load, mark 30 kilonewton. So at A it is 0, 30 maximum, and at B it is 0. Similarly, span BC. So span BC is WL by 4. BC, WL by 4. So it would be 120 kilonewton meter. So this is 120. Okay, so once you mark this, and here there is no external loading only. Okay, so then mark these final moments. So you can see here final moments is trying to push the beam inward, so positive side. So it is 15.35. Next, okay, this side it is acting outward, it should act outward, it is 56.1. Okay, negative side. Next, here also it is 56.1, which is acting upward. Okay, and here it is 25, acting upward. So here it is again in this portion, come down to this portion, that is 6.44, acting inward, and here it is acting outward, so 25. So plus and minus, so here also plus and minus, here minus and minus. Okay, All right, and this is 120, where whichever is above the line. Again, this is above the line, so you can see here this is all negative moment. Only this free bending moment exerts above the line. So this is, mark this as dotted, or hatch this. Okay, so this is the bending moment diagram from the given frames of sway analysis. Okay, again, in the difference between sway and non-sway analysis is, in non-sway analysis there is only rotation, that is theta b and theta c, whereas in sway analysis you need to find another third term, third unknown, that is delta. So that's why you have to find the delta, you need to find the, you need to separate the columns and find the given uh, equation, and finally substitute. So you'll get three unknowns, three equations. Mm. All right, that's all for today. Thank you.